Colloquium series. Today I have the pleasure to welcome a new faculty in the Computational Science joint program, and Ramin Bostanabad, who is actually going to talk about machine learning, artificial intelligence using materials and other things. So take it away.
Sure. Okay, let me share my screen first. Let's see. Okay. And I'm going to go full screen. So hopefully you guys have the presenter mode right now, okay?
Yeah, we can see it.
Yep.
Yep.
Okay. All right, thanks for the introduction. As said, my name is Ramin Bostanabad, and I'm extremely excited to talk to you about some of my recent work at the intersection of statistics, machine learning, and materials modeling. Now, the reason that I want to talk about materials modeling is that simply take a look around. Everything you look at is made out of something. That something is a material. The infrastructure of our cities, the way we provide energy, technology, transportation means everything relies on some sort of materials. And the thing about materials is that over the past couple of decades, they are becoming increasingly more complex. To use an example, I'm going to be employing fiber composites here. So over the past couple of years, we want to engineer fiber composites that are lighter, but at the same time stronger, tougher, and more wear resistant. If you notice, all these properties that I just mentioned are more often than not contradictory. So this essentially calls for a holistic perspective on understanding materials and coming up with efficient computational approaches to design them. Now, it is well established that structures and materials, which are in essence some sort of structures or systems, have a multi-scale nature. And to understand how they behave, we have to go all the way down to the microstructure level, in this case, and first try to understand how the microstructure or the building block of a material behaves. Once we have that understanding, once we can come up with some sort of a mathematical or a statistical representation for the microstructure, hopefully we can relate that microstructure to the property of the material. And that's done through the so-called constitutive law. At that point, if you believe that your microstructure has some sort of an uncertainty or randomness in its nature, you can take that randomness and propagate it through the constitutive law to see how your product or material at the scale of interest behaves in a random fashion. Now, this is a bottom-up analysis, which is used to analyze and understand the multi-scale nature of materials. But when it comes to engineering something or designing something, we have the targets or the property in mind at the scale of interest. So we have to take an inverse approach to designing something. And that has the issue of time complexity. In essence, the simulations that we have to use for materials modeling are extremely expensive. So we can't really use them for design unless we somehow speed those up. And this speeding up is essentially going to be done with machine learning. However, that's not the only thing we have to be careful about. We also have to consider the potential discrepancies between the simulations and the experiments or the actual physical phenomena or system that we're trying to model, because more often than not, our knowledge on the physical system is incomplete. Even if it's not complete, we have to make some sort of assumptions to simplify the system and then be able to model it. All of these assumptions or unknowns result into discrepancies. So we have to find a way to address those. So based on the topics that I just mentioned, in today's presentation, I'm going to be going over three major topics. The first one is on microstructure characterization and reconstruction, or for short, MCR. And I'm going to be talking specifically about a method based on deep learning that uses 2D images to extrapolate and generate 3D microstructures. Then I'm gonna, once we motivate the understanding of microstructure, I'm gonna be introducing you different methods that we can use to speed up or accelerate how we calculate the property of a material given the microstructure. And then I'm going to conclude the talk by the topic of data assimilation with Bayesian analyses. Essentially, what we want to do is to see if we have discrepancies between simulations and experiments, and if so, how we can address those. All right, so the topic of MCR essentially boils down to somehow finding a mathematical or a statistical representation for the microstructure of a material. I have two examples here. The one on the left is a crystal where different colors represent grains. The one on the right, I have the 2D SEM image of a porous material. The idea here is to come up with a function, either mathematically or statistically, that once you find it, you can take realizations from it, and each realization is going to give you a microstructure. Now, this is motivated by the fact that taking images from materials could be extremely expensive and time-consuming. For example, SEM-OT images. Sometimes we actually might have limited number of images or small images, but when we want to analyze them in computer, we have to enlarge them somehow. Then the question becomes, how can we go about, converting a 2D image, for example, into a 3D image, essentially extrapolating the knowledge with some mild assumptions? Or how can we come up either implicitly or explicitly with that mathematical representation? The methods that have been developed for this problem over the past couple of decades are, first of all, quite expensive and high dimensional and material system dependent. That is, if I have a method that works on the image you see on the left, I cannot really apply it to the image you see on the right. Let me quickly do this. Okay. Now, the idea that I was pursuing was to somehow use the capabilities and the flexibility of deep learning to address this issue. Now, to do that, I'm going to first introduce you to some topics of deep learning, and then I'm going to come back and see how it can help us to solve this problem. I'm assuming you have a basic understanding of deep learning. If you do not, think of them as a really simple way to connect a set of inputs to a set of outputs, right? So if in a shallow network, shallow feed-forward neural networks, I have the inputs to my system on the left-hand side, and I have the outputs on the right-hand side, and whatever is in between are called essentially the neurons in the hidden layers. Over the past few decades, over the past few years actually, we've been able to increase the number of layers that we can put between the inputs and the outputs. That's given rise to the so-called deep networks. The good thing about these networks is that they have great representational power. That means they can learn really complex relationships between the inputs and the outputs that you're interested in, whatever those inputs and outputs are. Now, this is the so-called feed-forward neural networks, but in computer vision, we are really interested in spatial features. And these kind of networks are not the best way to capture those features or model those features. In computer vision, we generally use convolutional neural networks, which are similar to feed-forward neural networks, except that instead of simply using matrix multiplication, you use the so-called convolution or cross-correlation operations. Now, I'm using 2D and 3D demonstrations here to show this idea. Essentially, what you're going to be trying to learn in a convolutional neural network are essentially a set of kernels. So what you're going to have to do is to design a kernel. That means the size of the kernel, which is nothing but a matrix, and the dimensionality of the matrix could be changed. In this case here, I have a 2D kernel. Here, I have a 3D kernel. The dimensionality of the kernel depends on the dimensionality of the input. Now, the size of the kernel is something that you as the designer decide, and the numbers are going to be determined during the training of the algorithm. But the way it works is that you have an input image, and you take a kernel and you sweep the input image with that kernel what you end up with is a response map or a feature map, right? So in this particular example, I'm just showing one of the numbers that I get in the response map. So this is the basic idea of, convolution. And in CNNs, you essentially have 3 building blocks. They are the convolution layers or convolution operations, which are shown here. And the other one is the pooling layers, which are used to reduce the dimensionality as we go deeper and deeper into the model. I have an image, I'll show it in the next slide. And then we usually have some dense layer at the end of the network, which are used for classification. Now, these models, CNNs, are extremely useful for different reasons. We can use them for object detection, for anomaly detection, classification, segmentation, and many other things. And we can also use them for stylistic purposes. So here I'm just using my image and I'm trying to impose an arbitrary style over it. So you can see how CNNs help us to not only do some meaningful jobs as shown on the bottom, but also something that could be of interest, just visually speaking. Now, the real beauty of CNNs is in their transferability, in a sense that there are people, let's just say at Google, Facebook, Amazon, or Apple, who have immense amount of resources at their disposal, and they have a lot of data, and they also have expertise into fitting these models. And once they fit the model, for whatever reason they want to use it for, we can use parts of their model for our purposes. Now, I will explain how to when we talk about the application, but at this point, I want to talk about one of the pre-trained CNNs that was perhaps one of the ones that was really performing well when it came to classifying images. So the network is called VGG19, and it has 5 distinct blocks. Each block, it starts with some convolution layers and ends with pooling layers. The job of the pooling layer, as shown here visually speaking, is to reduce the dimensionality of the response map as you're going deep into the model. So the depth dimensionality is essentially from left to right. VGG19 again has 5 blocks. In the early blocks, we have 2 layers, and later on, we have 4 or 5 layers. In each of these convolution layers, we have a set of kernels, which the model is going to learn as you train it on some training data. The job of these kernels is to extract different features from an input image, and those features could be anything. It's well known in the literature that deep learning is not really explanatory, so you might not be able to get a lot of information out of it. But recently a lot of people are working to address that, and in CNNs in particular, we know that the early features that we observe in the early blocks of the model essentially act as various edge detectors, right? As I'm showing here, the features that I get, the feature maps as I get in the early blocks are essentially edge detectors, or they detect the brightness at different pixels. As I go deeper into the models, the response maps that I get become more and more abstract. So as a person, I can't really say what they are. They obviously have some sort of an abstract meaning, but I can just look at them and then say, okay, this is an eye or an eyebrow or a building or something like that. It's their collection that means something to the model. Now let's see how we can use this idea for microstructure characterization and reconstruction. Now, to go and review the problem, what we're given is a 2D image of a microstructure, and what we want to arrive at is a 3D microstructure whose statistics are the same as the given 2D image. So we have a few tasks here. First of all, how to extrapolate from 2D to 3D using a pre-trained neural network. And second, how to get statistical features out of the network. So the question on the statistical features is actually a pretty simple one. All you got to do is once you feed in an image into VGG19, you will end up automatically with a set of feature or response map. These are automatically given to you. What you want to do at that point is vectorize these feature maps. So as I showed in the previous slide, there are matrices, right? Vectorize them and then put each vector as the row of a matrix. Doing so, you end up with the matrix of feature maps, which in my slides at this point is denoted by RLB. And at that point, you can calculate the autocorrelation between this matrix. Doing so, you end up with a statistical feature, which in the literature is known as Gram matrix. So right now, we have a statistical feature, and we want to preserve this statistical feature in the 3D structure. Now let's see how we can calculate these statistical features for a 3D structure, because VGG19 only accepts 2D images. Now the idea here is actually pretty simple, but its implementation is very tricky. So to get this done, what I had to do essentially was to trick VGG19 to think multiple stacks of 2D images are essentially come from the same microstructure. Because if you give VGG19 100 images stacked one after another, it's gonna assume that those 2D images are independent from each other, and it's gonna analyze them individually. We don't want that. We have a 3D structure, and there is a distinct spatial relationship in that. So to get this statistical feature out of it, what I did is I enforced VGG19 to look at my 3D structure from different angles. For example, I can rotate my structure in different directions, which is the permutation operation that I have here. And then once I rotate it, VGG19 is going to be used to extract the features from that specific angle. Now the figure that I have in the middle of the slide shows this. So given a 3D input, now let's just say I want the features to be extracted along those 3 orthogonal gray planes, right? With this approach, once this 3D image is inputted to VGG19, I'm gonna get these features. So on the first block, I'm gonna get this feature, which each of these is a 200 by 200 pixel. As I go deep into my model, the dimensionality of the features decreases. So I end up with, at the very end, which is the 5th block, I end up with images which are 12 pixel by 12 pixel on each side. So you see that the dimensionality decreased. Of course, the number of features increases. Now at this point, we have addressed both of the issues. So we have statistical features, and we can get 3D features out of 3D matrices, now, or 3D microstructures. Now let's see how we can go about enforcing these features into a 3D structure. Again, the idea is pretty simple. What we're gonna do is, we're gonna start off with a random microstructure, and then we're gonna try to adjust that microstructure iteratively, or one step at a time, in such a way that the statistical features of that 3D microstructure become as close as possible to the statistical features of the original given 2D image. And that's essentially what this formula at the bottom represents. It tries, this is the cost function, and it calculates the difference between the statistical functions of the original function, which is that G, the Gram matrix introduced in the previous slide, and the Gram matrix of the 3D microstructure that I get, for example, with this guy. In essence, the approach looks like this. So on the left, I have the flow chart. I'm given a 2D exemplar. In this case, this is the EVSE data. And on the right, I have a random 3D image. I'm gonna iteratively refine this image until its statistical features matches those of the given 2D example. And I end up with something like this. The beauty of this approach, as opposed to other approaches that were developed over the past few decades, is that, as seen on the right-hand side, it's applicable to a wide range of microstructures. So I have porous materials here, I have 2D images here, I have, at the bottom left, I have an image from AM. Again, it's applicable to a wide range of materials, regardless of whether you have a specific type of features in that microstructure. This essentially shows the power of transfer learning in microstructure characterization and reconstruction, right? Now that we have a capability of generating microstructures for modeling, let's see how we can actually model these microstructures and get some property out of it. To do that, actually, I put another example which I found interesting. So in this one, what I'm assuming is that I have an image. I have 3 images from different angles from a microstructure. So microstructure in the A is the original structure. And I'm going to take 3 images, each one from one side of it, and then I'm going to use those and learn the statistics in different directions for a 3D new microstructure. So A is the original one, B is the reconstructed one. If you compare them section by section, they look the same. They're not exactly the same, and that's not the point, but their statistics is the same. And I'm going to be comparing them again, for example, the distribution of the grain size. And as you see, it's preserved pretty well. Now let's see how we do the simulations. To motivate this, I have to introduce something known as multiscale simulations. Recall that I said materials are multiscale, right? What that means is that if you want to analyze, let's just say the deformation of a material, the one that I have here is a woven matrix, woven fiber. What you're gonna have to do is essentially discretize that with, let's just say, finite elements. Once you discretize, you end up with some elements. Now, if the material is a simple material, at that point, you can simply link the applied deformation or strain to stress. If, however, the material is complex, which is the case here, you cannot simply link the strain to stress. What you have to do is to take a microscope, look closely at that element. If you do, which is what I'm doing here, you would see a lot of heterogeneity in the microstructure. What it means that you have to, again, mesh or discretize the structure. So you have 2 sets of discretization, one at the coarsest scale and another one at the finest scale. Now, when you're deforming a material, you essentially want to solve a set of partial differential equations. Now, imagine you have 1,000 elements at the coarsest scale, so that means you have to solve 1,000 partial differential equations. For each partial differential equation you want to solve, let's just say at this point, you have another structure. Let's say you want to discretize this one as well to, say, 1,000 elements as well. You end up with 1,000 PDEs here. So you have 1,000 PDEs. Each of them, again, is connected to 1,000 PDEs. That's just a lot. We cannot do that, right? So the idea here is that these simulations are extremely expensive, and we're looking for a way to speed them up. And there are different ways to speed these processes up or simulations up. It really depends on the material system and how it behaves. For example, in this case, I'm interested in modeling a hyperelastic material, whose strain increases, or store potential increases, as I increase the amount of applied strain or deformation. Now, what I want to do here is to come up with a surrogate model, or a supervised learner, if you will, or a response surface, that I can train it on with some inexpensively obtained simulation data, but then I can use it to predict the behavior of material at largest strain. So I'm going to get some training data at smallest strain, and then I'm going to try to extrapolate the behavior to largest strain. Let's see if we can do this and under what conditions. So the idea is very simple. What we want to do is we're going to do some simulations offline, and then we're going to try to learn as much as we can from those offline simulations, essentially learn a response surface, and then use that response surface into the finest scale simulations. And this is how it's going to work. First of all, we have to understand what's changing in the system of interest. So if the microstructure is changing, we have to generate a set of microstructures. If we expect the microstructure to go under different loading conditions, we also have to generate different loading conditions. This is the so-called design of experiments, right? So we're going to design experiments. We're going to run a bunch of simulations using, in this case, finite element analysis. And then we're going to do machine learning. We're going to try to link the inputs, whatever they are, to the outputs. This is the idea, and I'm going to be talking about 2 different ways, essentially, for doing the machine learning, which essentially depends on my material system. So the first example is going to be on hyperelastic materials. The behavior of a hyperelastic material at any point in a space depends on where you are at that state. It really doesn't depend on how you got to that state. And that essentially means that I don't really need to care about the history of the material, which significantly reduces the dimensionality. Now, there are many ways to do response surfaces or build response surfaces. One of the most efficient ones is Gaussian processes. If you're not familiar with them, think of a Gaussian process as a natural extension of normal random variables. If you have a normal random variable and you take your realization from it, you end up with a number, right? But if you have a Gaussian process and you take your realization from it, you end up with a function. Now, the idea here is that to learn the parameters of a Gaussian process in such a way that once you take realization from it, those realizations follow a certain trend. Now, that trend is going to be dictated by the training data. Now, the way you should go about fitting a Gaussian process generally involves assuming some sort of a parametric form for the mean function and the covariance function. Remember, for a normal random variable, you had the mean and the variance, and you had to estimate those given some sort of training data, right? In this case, I have a mean function and a covariance function. So these are not just numbers. Once you have those parametric functions and given some sort of data set, you would use the method of, let's just say, maximum likelihood estimation to estimate those parameters. Once you estimate the parameters, you can use the formulas at the bottom of this slide to not only predict the response of interest at any point you want, but you can also predict the uncertainty or randomness associated with your prediction, which is also schematically shown in this figure. Now, the issue with Gaussian processes or any response surface modeling you want to pick, it could be trees, it could be polynomials, it could be neural networks, whatever you want, is that they have issues with extrapolation. For Gaussian processes, that depends on this function f. We generally don't know the trend of the data, so we don't use any parametric mean functions. We just use some constants, betas, and we let the algorithm estimate those constants by its own. This works perfectly fine as long as you're doing interpolation. So here I have a schematic figure that shows I have some noisy training data. If I'm doing interpolation and if I'm fitting a Gaussian process, I can learn the true function really good. But as soon as I try to extrapolate, I'm going to run into issues because the Gaussian process is going to revert to its mean. And the idea is that the prediction formula has two parts. As you get away from the region where you had training data, the contribution of the second term diminishes. So what you're left up with is this beta hat. Essentially, you revert to the mean, which is this beta hat. So to address this, what we have to do is to essentially estimate somehow some parametric functions. If we can estimate them correctly, we can do the prediction pretty well. Now the question becomes, how can we actually estimate these functions? Now to do that, I'm gonna be using evolutionary programming. It's very simple to genetic algorithm, if you're familiar with that, but it's applied to either symbolic regression or actually dynamic program. So the way it works is that you start off with some simple functions like sine and cosine and log and exponential, and then you try to combine them in different ways, for example, a crossover and mutation and so on and so forth, and then evolve them through some sort of an evolutionary approach such that the resulting function can reproduce the training data in a good way. So this is the basic idea of evolutionary programming. And it was actually introduced more than 2 decades ago by Kotza for learning some, so essentially training some robots to do some specific tasks. However, it has some limitations. In particular, it's not really applicable to high dimensional problems. If your training data is noisy, it's going to run into issues or overfit the data. And it also has an issue with convergence. So there's not a systematic way of detecting whether or not we should terminate the iterations or evolution of the function, or we should just continue and when we should end it. So to address this, we have actually a very simple approach. So given some sort of training data, what I'm going to do is I'm going to fit a very simple Gaussian process. And then I'm going to use that Gaussian process to generate some training data for EP. This has two advantages. The first one is that with a GP, if I'm really very smart about it, I can easily get rid of noise. So I'm going to smooth out the data. And the second thing is that once I have the GP, I can use it to generate data for EP in the way that best serves EP. So for example, if I know that, again, I'm interpolating here, I'm not extrapolating, so GP is fine. If I know that in some region of the input space, I have very nonlinear behavior, I can generate more training data with my GP in that region, because my original training data might not have a lot of information in that region. Once I do EP, I end up with some parametric bases. I don't know if those bases are correct or no, so what I'm gonna do is I'm gonna refit the GP, but this time I'm gonna use the parameters found by EP. At this point, GP is gonna tell me if those parameters are correct or no, and it does so using the method of maximum likelihood estimation. So if a parametric basis proposed by EP is incorrect, the maximum likelihood estimation of its coefficient is going to be very close to 0. And if it's not 0, we have a systematic way of detecting it, but I don't want to get into the details at this point. So we go through this loop over and over again until GP starts to learn noise. Now, the question becomes, how can we detect if GP is learning noise? Again, this could become a little detailed, but the point that I want you to take away from this is that if you are careful about how you fit GP, if you're fitting your GP correctly, the parameters of the correlation function will clearly tell you if you're fitting, if you're essentially trying to learn noise. Two things are going to happen. If you're trying to learn noise, and if you do a GP in a good way, the parameters, your GP essentially is not going to learn anything, right? Which is essentially shown here. So I'm going to be regressing some noisy data. This is the correct way of modeling noise. You're not going to learn anything from it. In this case, the parameters are going to be super small, essentially signaling there's nothing I can learn. If, however, you're not careful about how you fit the GP and you end up interpolating noise, that's also fine, because in this way, the parameters you will get are going to be super large, again, signaling your learning noise. That's essentially our way of terminating the approach. So we have a recent conference paper on this where we compared EP in and of itself with our approach, and we were trying to figure out if we can actually retrieve these symbolic functions. And as shown on the right, and this is just part of the studies that we did, as shown on the right, in all of the cases, we can do a good job in retrieving the true functional form. Now, in reality, we don't know if there is an underlying functional form. So what do we do? In that case, we can actually use some other knowledge. For example, qualitative knowledges that we have on the system to realize if we're actually doing a good job in learning the relationship between the inputs and outputs. Now, let's go back to the material system example. So the material that I have here is a heterogeneous and incompressible microstructure. Heterogeneous essentially means that the microstructure looks pretty messy, which is evidenced by the image. And incompressible, it means that you cannot compress it. If you try to compress it, you would store a lot of energy in the material. Now, our material is also hyperelastic. It means that it has a potential of 0 when strain is zero, and as you apply a strain to it, the potential is going to increase, right? So either compression or stretching, you're gonna store energy in the material. But since it's incompressible, if you try to compress it, you would store more energy into it. Now, the inputs here are essentially the principal strains that we apply. So we have two inputs. And the output is the potential, which always has to be positive. The data that we have comes from expensive finite element simulations. And in particular, we have 512 samples. Now, again, I don't want to go into the details, but what we ended up doing was we took the training data and we fitted different response surfaces to the training data, and we wanted to figure out which one performs good in extrapolation. In particular, we used polynomial regression, cross-validated polynomial regressions, GP alone, EP alone, neural networks, and our approach. as I'm showing here, the only case where we actually get a really nice curve which preserves our qualitative knowledge on the system is the one obtained by our approach. And we actually can get the confidence intervals that characterize the uncertainty in the material. Now, the example that I have here relies, or the assumption that I have here is that once I'm extrapolating, the physics of the problem doesn't change. So whatever physics I have to learn, I can learn it from that interpolation region. For example, if my material is going to fracture at some point, I cannot predict it with this model because essentially I don't have it in my approach, right? We're not discovering the new physics, we're just preserving the physics that there already is in the data. Now, this was a rather simple example, I would say. A much more difficult example is the case where the behavior of a microstructure depends on how it's deformed. So let's just say I have a microstructure shown on here, on the right side of the slide, and I want to go from point I to point E. The state of the microstructure is going to depend how I go from I to E. In this case, for example, the path that I take. So this becomes extremely difficult to model because there are infinite number of ways that I can go from I to E. Then the question becomes, okay, how can I quickly predict, given a path, an arbitrary path, how can I quickly predict what would be the state of the microstructure at E? So this is the so-called history-dependent deformation of materials, or plasticity. So plasticity is a type of deformation where you have some sort of a constant deformation in material. So it's not reversible. And it's also path-dependent. To model this, we use a specific kind of deep learning models known as recurrent neural networks. I don't have detailed slides on it because it could get a little messy, but I will explain what they are. So in convolutional neural networks, we're interested in capturing spatial features, right? So for example, learning an edge or an eye wherever that edge or eye is in the image. With recurrent neural networks, or RNNs, what we want to learn is the relationship in sequences or in history. So if you have, for example, a process or some sort of a time series, RNNs are actually the way to understand how that time series changes, how the dynamic is evolving through time. And this is what we're going to be doing here. So again, using the data-driven approach that I motivated a few slides back, what I want to do essentially here is generate potential deformation paths that I can have from I to E. So I can generate, let's just say, 1,000 or 5,000 deformation paths from I to E. I'm going to try and learn an RNN that can tell me how the state of the microstructure is going to be at E, given a deformation path. And once I have that RNN, I can use it to predict the state for any given deformation path. Let's see if we can actually do that. So here's what we did. We started off with actually a very simple microstructure to show that the approach works. So the example that I have here is a matrix, a two-phase material essentially. The matrix is shown with essentially nothing, and the filler is this smiley beam. What we did was that we deformed this structure in 15,000 different ways, so 15,000 deformation paths. And then we fitted an RNN to try and see if we can actually learn the dynamics or the deformation mechanism of this simple microstructure. Now, the method that we use to generate the deformation paths is actually an extension of the traditional design of experiments. Because with design of experiments, you would generally design scalars. For example, x equal 2 or 5 or 8 or something like that. But here, you have to design a path. So it's not a simple scalar. To design the path, I actually used a Gaussian process itself. As I said before, a Gaussian process can give you a function. You just have to tell it what kind of functions you want. Now, by nature, a Gaussian process is going to produce fluctuating paths, as I've shown on the right-hand side, right? Now, the idea here is we want to cover as much of the input space. Now, input space, again, is extremely high dimensional, infinite dimensional again, because it's path. but we're going to try our best to cover as much as we can. Let's see how it works out. Now, to test it, essentially, what we're going to do is that we're going to take the same microstructure and deform it in two different ways. The first way is given a random load path, which is similar to how our training data is generated. And then we're going to calculate the stress or the response of the material in two ways. The first one is with RNN, or the model that we have trained. And the second one is with FEA. The difference between these two, however, is that FEA takes, I believe in this case, it took somewhere north of 20 minutes. But with RNN, once we fit it, it's almost instantaneous, the prediction time. Now, the second one, which is more interesting, is a unidirectional loading. In this case, the deformation is not fluctuating. So we just go straight up and straight down, which is definitely not in our training, because we use GP in our training. And as I said before, inherently GP generates fluctuating paths. Now, we try to predict stress and also the stored energy in the material. And as you can see, we're doing a really good job in predicting the stress. And what's also important is that we're learning that Poisson ratio or Poisson effect, where I'm only applying the stress in one direction, but because if you stretch something, it's going to shrink in the other direction. You also have stress in other directions of the material. Now, again, we took a step further and we wanted to see if we're actually learning the physics of the material. To do that, we looked at something known as yield surface. So if you have a material and you stretch it and it yields, it actually becomes stronger. So it becomes a little stronger until you actually, for example, stretch it too much that it breaks or fails. So we wanted to see if we're actually capturing the evolution of this so-called yield surface. And as shown on the figure here, our RNN is actually learning that quite effectively as well. Now, to take a step further, in the previous example, I didn't change the microstructure. The only thing that was changing was the loading path. Now, in this case, I also want to change the microstructure. So some sample microstructures are shown on the right, and a sample loading path is shown on the left. So in this case, I want to see, given a random microstructure and a random loading path, can I learn the relationship, or can I predict the stress? Same thing, we generate to do the validation, we do the same thing. So I generate a random microstructure, and I take it into two different deformation paths. In each of them, we're doing a really good job in terms of predicting the stress as compared to true solutions. That true solutions come from, again, finite element simulations. Now, to this point, I just talked about the importance of microstructure and how to use computer simulations to calculate the properties of a given microstructure and how to speed those calculations up. But the question now is, can we trust those calculations? And if we know for some reason that those calculations are off, is there a way, a systematic way to correct them? To do that, I'm going to have to introduce a new topic known as data assimilation or data fusion or model fusion. Essentially, we have multiple sources of information and we want to combine them. To motivate that, I'm going to use the thermoforming process in fiber composites. So essentially, we have a set of fiber composites. We put them on a press machine and then deform them to get to the ideal or the desired shape. In this process, something known as fiber reorientation happens. Sometimes it's not desirable and it leads to local stresses, which later on result into failure of the material. So we want to develop a computer model that can handle this kind of process. The model that we have to develop is, again, multi-scale. And in this slide, I'm essentially showing how it works. But the issue with our model is that, first of all, it has some calibration parameters. In particular, to run our computer model, we have to know some of the material properties, but we don't know those, or we cannot directly measure those, which are E1, E2, and mu. So E1, those E's are ions moduli, different directions, and mu is essentially the coefficients of friction between the yarns in my fiber composites. So that's the first issue. I don't know these material properties. The second issue is that I know that I'm missing part of the physics in my computer simulation. Either I don't know some of them, or some of them are just too complex to implement, right? So how can I address those? How can I build a computer model or a surrogate model, as I did in the previous slides, while acknowledging these sources of uncertainties? Now, the data that I have is actually on multiple scales. So at mesoscale, I have some experimental data that can tell me how the material behaves at the mesoscale. I'm going to go back quickly. So mesoscale is this finest scale. So the smallest scale in this example is called mesoscale, and the larger one is called macroscale. So I have these data. So uniaxial tension and bias extension. I'm going to try to speed up because I only have a few minutes. And then what I here tried to do was to try to simulate the computer model and change the parameters, trying to see if I can match the experimental data. I couldn't, which further shows that I'm missing part of the physics of the problem. Now, the way that I want to combine the experimental data and the simulation data is through the so-called Bayesian analysis. The reason we want to use Bayesian analysis is because it allows us to quantify or take into account multiple sources of uncertainty, including noise, unknown parameters, missing physics, lack of data, and so on and so forth. There are different ways to go about Bayesian analysis. A particular one which is extensively used in the literature is that of Kennedy and O'Hagan, which they essentially model the system as this. So I have the physical system on the left, I have the simulation here, and I'm missing some residual function and noise. So the task here is to learn these parameters, these scalar parameters, thetas, plus this function delta, which is the missing function or missing physics. The approach that Kennedy and O'Hagan proposed is fully Bayesian, but I developed a modular Bayesian approach because it's faster, it's more robust, and it allows me to build in some physical knowledge that I had from the material system into the analyses. I don't have the time to go into the details. Hopefully someone asks questions so I can come back to this, but here are how the results look like. So in the first module, what I have to do is something similar to what I taught before. I want to replace my expensive computer simulation with a surrogate model while I actually impose some physics into the problem. So this is how the surrogate model looks like. So essentially it's stress as a function of strain with and without physics. You see the advantage of using a modular approach, which enables me to build in physics and in turn be able to fit a better response surface. In module 2, I'm going to be using this along with with some assumptions that are built into my Bayesian analysis to come up with the posterior distribution for the calibration parameters. So the calibration parameters are shown here, E1, E2, and mu. And the blue curves are essentially the marginal posterior distribution. It essentially, as opposed to giving me a point estimate, it's giving me a distribution. And the distribution in this case is actually pretty wide, which is okay because I didn't use much data to come up with a posterior distribution anyways. Then I can use the models in my Bayesian analysis to come up with the posterior distribution of my responses. The responses being the stress as a function of strain values, which in this case, I'm going to be validating those against some data at the mesoscale that was not used in the training. So I had two data, tension data and bias. I used tension for calibration, and I'm going to be using bias for validation. As shown here, we're doing a really good job in terms of matching the experimental data at mesoscale. Now, we're going to go one step further and do actually a multi-scale simulation. So the model that I had previously is going to be used in finite element analysis as a constitutive law. And then we're going to do another set of validation. In this case, we're going to be measuring the global distance or global deformation of the material. And we're going to be comparing our results against an older method that was out there in the literature. As shown on the figure on the right, we're actually doing a really good job in terms of measuring the required force in that preforming process. We can also do a local validation. That is, as I said before, reorientation is important in fiber composites. So once we do the simulation, we can calculate and see how much reorientation we have, and then compare those with experiments. As shown on the table here, again, we're doing a better job as compared to the previous models. So what I want you to take away from this presentation is that materials need a holistic perspective when it comes to modeling them and designing them. And this holistic perspective relies on at least quite a few fields. In this talk, what I was trying to do is essentially motivate the use of machine learning and statistics in analyzing solid mechanics of materials. So with that, I'm gonna conclude the talk, and thank you all for your attention, and I'm gonna open up the virtual floor for questions.
Well, thank you very much. So I'm gonna pass the baton to Sachi, who I think is now there.
Thank you, Hussein. Thank you, Ramin. Sorry, we had a hiccup that made me join late. Let me see if there's any questions from the audience before I jump in. If you have a question, please unmute yourself and you can ask the speaker.
Sure, please go ahead.
Okay, so I had a question, and I'm a little bit curious about this physical constraint that you managed to impose. What is there? Obviously, when there was things in your simulation that you don't capture all the physics, right? You have a empirical knowledge deficiency. So what is it that you bring in then later on for this problem?
So one of the things that we wanted to address was lack of data. So, and also noise. So some of the simulations that my collaborators were doing, Jin Chao's group in particular at Northwestern, their final element simulations every now and then had some noise due to severe mesh distortion. So that was one of the issues. The second one was lack of data. Because again, the simulations are extremely expensive. So one of them on a HPC takes around, I guess, somewhere around 30 to 40 minutes. So we can't do a lot of them. Now, a lot of parameters are changing here. So I have 6 parameters that I want to put in my surrogate model. So I have 3 calibration parameters, E1, E2, and mu. And I have the strains, right? Epsilon1, epsilon2, and epsilon1, 2. So 6-dimensional function. And I think I had around 200 training data. So once you fit some sort of a response surface, you would see some fluctuations that physically don't make sense. For example, if I'm in the early stages of the deformation and I'm increasing the strain, I expect the stress to just go up monotonically. So if I see fluctuations or waviness in the response surface, that's just physically not meaningful. What that means is that if I want to put it or use it as a constraint in my training, I can ask my or I can constrain my response surface to have a positive gradient. So that would be essentially the constraint you put into the training process. Same thing applies if you're using some sort of a deep learning approach. So you can regularize essentially your cost function or loss function with whatever information you have from the physics of the problem. In the example on the plasticity, learning the plasticity, we actually used our knowledge on the physics for validating the RNN. It's also a little bit tricky to enforce those into training.
Okay. So coming to that last bullet on it, system agnostic, that's a big claim, right? That is, that says irrespective of what material system and things like the overall methodology should still work.
To some extent, it is the case, right? Except for cases where the limitations come from either not being able to use GPs. For example, if you have history dependence, using GPs for that is very tricky. And I would go for an RNN for sure. Another one is if the underlying assumption is actually not correct. So if I go back, the underlying assumption here is that, let's just say this is my experimental data, Z of X, or actual physical system. This is my computer model. This is a discrepancy, and this is noise. Now, if what you're missing is not really a residual, but it's really more than that, then the underlying assumption is incorrect. right? So the approach is going to fail. So there are some basic assumptions that go into the approach. Another one is the use of multivariate normal distribution. So because that's the way we come up with the likelihood term, right?
Mm-hmm.
So there are some steps that we need to take to make sure that the approach is applicable to the problem of interest. Sometimes, even if they are not met, for example, the constraint on multivariate distributions, even if it's not normal, maybe we can do some sort of transformations using, for example, Rosenblatt's transformation, which is, again, it's not easy, but we can do it, to satisfy those constraints. Other times, it's just too complex to satisfy. So we sometimes just go with other methods, because the approach that we have here is, it's going to work, but it doesn't provide us with correct solutions.
Okay, thank you. Questions from the audience? A lot of people there.
Well, we're not taking this gentleman out for a beer, so I just thought I'd toast him with my spiked soda.
Thanks. I have my drink here too.
Yeah, but mine is spiked soda with organic booze. You only do these things. I mean, instead, if you went, well, if you had been taken out for a beer afterwards, would you have just ordered milk? Just curious.
It really depends on the environment, right? And who's accompanying me. So if everyone orders water, I'm just gonna go with, I don't know, water probably.
Okay, well, it was truly, verily, mathematically groovy. So that's all. I'm gonna mute myself now and enjoy the Christmas lights. Okay, have
Thanks.
fun.
Thank you, John. Ramin, if I may, can I ask one more question?
Sure, please go ahead.
And this has to do with your calibration versus your validation data sets.
Mm-hmm.
I understand you need to have separation of these two, and so you're taking unidirectional test data for your calibration.
Mm-hmm.
But you're assuming inherently in that there's no interaction parameter that arises when you go to angle plies. Right?
So there is. So our approach, so if you, I was way too quick on this, but the original FEM model that we were using is a decoupled model, right? There's no interaction. But the new approach that we have, the details on the paper, is a coupled model. So that essentially took care of it. Just because there is that coupling effect in the way that we modeled fibers and fibers within the yarn, we were able to use one set of experiments and then be able to reproduce the other set. But then, yes, you're absolutely correct. So if we were to go with the decoupled model, which is the old approach, there was just no way that we could capture it.
So you could calibrate the angle ply response with just uniaxial data with the coupled model?
Yes, in this particular case, yes.
Okay, because I would, just from the sheer deformation of those fabrics, there's a lot more going on in angle ply than you would see in the uniaxial kind of couple, kind of puzzled how that works.
So, okay, so this is how the test setup looks like. So when we're uniaxially essentially deforming the structure, which is our mesoscale structure, essentially, we do get the effect from the shear and also the friction, because the yarns, you know, the angle between the yarns changes, right?
Okay.
And that is essentially what we're trying to model in our coupled approach. I think the paper is, let's see. Do I have, yeah, so this is the paper. So it essentially has two unique components. The first one is on how we actually developed that coupled deformation simulation setting, which then allows us to do this Bayesian calibration approach. And the Bayesian calibration approach, to get it to work, we have to modularize it and then enforce our physical knowledge in different parts and then use it for the multi-scale simulation.
So in terms of data assimilation, I was expecting to see something that if you have history-dependent process and you have experimental data, what is it that you're assimilating into the model from the experiments, besides the calibration part, on the history-dependent part? What is the
Yes.
when you say assimilation, is during the history you use data to correct and predict forward, right?
So different parts to that question. So let me try to address this part. The true simulation setting that we have, which relies on this part, where we're actually trying to model that punch force, right? Or the act of the press machine. That process itself is permanent, right? So it involves plasticity. Mm-hmm. But the majority of the approach that was used in our collaborators code, just because of the sheer complexity, was on linear elasticity. That introduces the so-called bias that I talked about, right? So we said that there are two sources of uncertainties in particular that we were interested in. The first one was unknown parameters, and the second one was the misrepresentation of the physics, right? Some physics we're misrepresenting, some physics we even don't know that we're missing, right? That's part of it. And the fact that the delta function that we had was, its posterior was not 0. So if I go back, you see that for the uniaxial tension data, if I want to reproduce it, the bias function is, relatively speaking, is pretty small. So it goes all the way to, let's just say, 15, while the actual data goes up to 150, so 10% maximum difference. But for bias extension, it's actually very large. So the magnitude is 4, and here the magnitude is 15. So it's almost like, what, 25%-ish, right? So that means that actually I am missing part of the physics. One of the caveats that you have to take in mind when you're doing Bayesian analyses is the problem of identifiability. To quickly explain what it is, I'm going to go back here. You see that for a specific value of theta, I can change the delta such that the right-hand side matches the left-hand side. So implicitly, what you get for the bias also depends on what you get for calibration parameters, right? So this is the non-uniqueness or identifiability issue associated with this approach. And it's well studied in the literature. There are different ways to address it. Adding physics, as we did, is one of them. But the beauty of the approach is the collection on the right-hand side works. So regardless of that identifiability issue, if the residual is in fact at least close to being a residual, the right-hand side is going to work. And it's been well documented in the literature, so many people have used it in the past. Now with more data that we have, people are usually going after deep learning-based approaches, which is reasonable. But in our case, we really didn't have much data. So for us, it didn't make sense to go after deep learning-based approaches. Does that answer your question, or?
Yeah, thank you.
Sure. Any other questions?
I guess not. In that case, we're gonna thank our speaker one more time. It was very interesting, very educational and interesting talk. And we usually take the speakers. Just hold your horses. We usually take our speaker for a beer afterwards, so we're going to have to do it next time when the thing is open and you come back.
Thank you. Thanks for having me. And hopefully we'll have some sort of a in-person discussion in the future.
Yes.